Hi, welcome to Chem with Chem. In this session, we're working question 1 of the CXC CSEC Chemistry Paper 2 from the January 2019 edition. If this is your first time to the channel, then welcome. Please check out all the other materials that are here. Like if you find value, and don't just leave it there. Share with a friend and consider subscribing and turning on post notification by hitting the bell so you'll never miss out each time new content like this is added. Let's dive in. Now, question 1 is a data analysis question, as is normally the case, and we're being recommended not to spend more than 30 minutes on this question. Let's go. An experiment was carried out to determine the percentage of iron in an iron salt sample. A 0.500 gram sample of iron salt was placed in a conical flask. To it, 25 mils of dilute sulfuric acid, 10 mils of phosphoric acid, and 8 drops of an indicator were added. The contents of the flask were mixed and titrated against a 0.02 moles per dm cube solution of potassium dichromate until the endpoint was reached. The ionic equation for the reaction is given below. Dichromate plus 6 Fe2 plus, that's iron 2 plus 14H plus to give 6 Fe3 plus, 2 chromium 3 plus, and 7 moles of water. Figure 1 shows the burette readings of the initial and final volumes of each titration. All right, so we're asked a little later on to read and record the values from what is shown in figure 1 for the burette readings. So just to minimize us scrolling, we're going to just record these values from now. So we're just going to read them off and have them on hand, and then we're going to put them in our table on page 5. That's table 1. So we're just going to read these off, then we're going to go back to part 1 where we list the apparatus that would be necessary to carry out the experiment. So we're looking at the burette here, and as is customary, whenever we have an instrument that has gradation and we're reading, we need to just figure out what the scale is, how much we're going up or going down by, what each of those little marks represents. So each of these little markings represents here 0.1 centimeters cube or 0.1 milliliters. So it means then that for the initial reading for titration 1, which is considered the rough titration, the initial reading, the reading there would be 2.00. And for the final reading in titration 1, we're looking at, this is 21.95. The initial reading for titration 2 would be, that's 1.85. And the final reading in titration 2 would be 21.85. That's right. Our meniscus, the bottom of our meniscus is in between the 8 and the 9. All right. The initial reading for titration 3 would be 1.50. It's sitting exactly on the 1.50 mark. And the final reading would be 19.50. So just make a note of those. We're going to, let us fix this so it looks like an 8. We're going to come back to these in short order when we fill out our table on page 5. Part A. So we're doing a titration. They already told us that we're doing a titration. They already told us that we're using a conical flask. And they're asking us to list the apparatus that would be necessary to carry out the experiment. They've given burettes already, or the diagrams of the burettes are, well, there's a diagram showing burettes, so I don't know if we should put burettes, if that is, if it's assumed that burettes are there. So we're going to list what the other materials that we would need in order to carry out this experiment. So we would need volumetric pipette. We're not just going to say volumetric pipette or just say pipette like that. All right, we have conical flask already. So it's fine, we don't need to put back conical flask. They said that conical flask is there. The contents of the flask were mixed and titrated. That's not where it was. Right, so they said it in the second line. 0.500 gram sample of iron salt was placed in a conical flask. To it, 25 mils of dilute sulfuric acid. Right, so we have the conical flask. So we'll need burette. We need a 50 mil burette, even though, you know, where burette is there, so it's a given. So we need a volumetric pipette. Conical flask is there. We're going to need a filter funnel. That's to fill the burette. We're also going to need a clamp and retort stand for the burette. All right, and that should be it. 2 marks. Okay, so the values that we just read off on the previous page for the burette readings, we're going to put them here, and we're going to find the volume of solution used in each case. So all the 6 values that we just read, we're going to fill them into our table. So use the information in figure 1 to complete table 1. All right, so in titration 1, the final volume was 21.95. The initial volume was 2.00, and the volume used would be final volume minus initial volume, and this would give us 19.95. In titration 2, the final volume was 21.85, and you can always scroll back to verify. The initial volume was 1.85. So 1.85 from 21.85 will give us 20.00. Titration 3, the final volume is 19.50. It can be read to 2 decimal places. The initial volume, 1.50, and so the final volume is 18.00. Now we get 9 marks for doing that. 9 marks, lovely. Part 1 of C, use an asterisk to, to indicate the titration data that should be used to obtain the average titration volume of potassium dichromate used in the experiment. All right, so normally when we're doing titrations, we want to get, it's great, it's awesome if we get identical values. That's not always the case. So we aim to get the next best, values that don't differ by more than 0.1. Now, looking at these 3 values, the variance between 20 and 18, that's big. So we would not use 20 and 18, despite them being consecutive. All right, so when we look, compare 20 with 19.95, those are close. Those actually differ by less than 0.1, which is great. So even though, you know, the first titration is normally the rough titration, as we saw on the page, the previous page, that titration 1 was the rough one, there's nothing that says we cannot use the values from titration 1. At the end of the day, it depends on the internal agreement among the values. And here we are, we're seeing where these 2 readings are close in that they don't differ by, they differ by less than 0.1. They differ by 0.05. So we're going to use those 2 readings, titration, the volumes from titration 1 and titration 2. So we're going to bear these 2 readings in mind, and we're going to apply it to the questions that follow. Part 2 of C, hence calculate the average volume of potassium dichromate used in the experiment and record the value to 2 decimal places. So that would be 19.95 plus 20.00. All of that added, then divided by 2. And our final volume is or average volume, 19.98 centimeters cube, or milliliters, same thing. Part D, using the information from C2, calculate the average number of moles of potassium dichromate used in the experiment. The average number of moles. So we'll have to go back to the concentration of the potassium dichromate. So the average number of moles used, we'll have to use the average volume here that we got in part 2 above. And we're going to be working with the concentration of the potassium dichromate solution, which we know to be 0.02 moles per dm cube. The big M there represents molarity. So there's a formula for this, so we can just cite that formula and then we punch in our numbers accordingly. So the formula says moles is equal to concentration, which is in moles per dm cube, times volume. Concentration times volume. And volume here is in dm cube. So we'll have 0.02 moles per dm cube times, and we're going to be converting our 19.98 cm cube to dm cube by dividing by 1,000. So that would give us 0.01998 dm cube, 3.996 times 10 to the minus 4. Of course, dm cube would cancel out per dm cube, so our final answer, the unit for our final answer there is mole. So that's 3.996 times 10 to the minus 4 moles. Now, the next question, part E, says, from the equation given on page 4, determine the number of moles of iron ions, that's Fe2 plus, that react with 1 mole of dichromate ions. Now, we're just going to write down that equation so we don't have to scroll. So the equation said Cr2, so dichromate Cr2, 0.7 2 minus plus 6 Fe 2 plus. We could pretty much stop there because the answer is there. Let's fix that. So that's 6 Fe 2 plus 14H plus to give 6 Fe 3 plus 2 Cr3 plus and 7 water. So we're concerned about, from the question, we're concerned about chromate and iron, the mole ratio of chromate and iron. So they're asking us to determine the number of moles of iron, that's Fe2 plus, that react with 1 mole of dichromate. So if we look to the left of dichromate, nothing is there. And if we see nothing there, it means that our coefficient is 1. or stoichiometric value is 1. So just like in math, when it's 1x, we don't say 1x, we just say x. So we're seeing that for every one mole of chromate that is there are 6 moles of iron. So we just need to say 6 moles, and that would give us our mark. So that would be 6 moles. All right, so we're going to take these values that we have and we're going to apply them to the following question. So the next question, which we'll look at shortly, F says calculate the number of moles of iron in the iron salt sample. So we know the number of moles, where is this now? We know the number of moles of dichromate that was used. Yes, we know the number of moles of dichromate that was used. We calculated that in part D and we got it to be 3.996 times 10 to the minus 4. And we said that for every 1 mole of dichromate, we had 6 moles of iron. The mole ratio of dichromate to iron is 1 to 6. So let's see what this would mean for our next question. So we just mentioned, or we just saw that 1 mole of dichromate reacts with 6 moles of iron. So the number of moles of dichromate that was used from our calculation in part D was 3.996 times 10 to the minus 4. So the number of moles of iron that's used in the sample would be the 3.996 times 10 to the minus 4 moles multiplied by 6, which would give us 2.3976 times 10 to the minus 3 moles. I could have rounded that. We could have rounded that to 2.4. Yeah, we could have rounded that to 2.40. All right. And then we move on to part G. Calculate the mass of iron in the iron salt sample. And they give us the molar mass for iron as 55.8 grams per mole. So mass, so this is a mole to mass conversion. So mass is equal to number of moles times molar mass. So it's a number of moles that we have in F, which is 2.3976 times 10 to the minus 3 moles multiplied by the molar mass, which is 55.8 grams per mole. So the per mole would cancel out the mole and would end up with grams. When we do that, we will have 0.13 grams of iron, Fe. Now, they want us in part H to calculate the percentage of iron in the iron sample. And if you recall, you can always rewind, you can touch it back to see the mass of the iron salt that was used. The mass of the iron salt that was used was 0.500 grams. And we just found that the mass from our calculations that, that was done using the titration, the mass was 0.13 grams. So to calculate the percentage of iron in the sample, it's the mass that we got, which is 0.13 grams, divided by the mass of the sample that was used, which is 0.500 grams. And we're expressing that as a percentage. So we'll have to multiply by 100, which would give us 26% for a mark. Part I, the reaction between iron and dichromate is considered a good reduction oxidation reaction. Define the term reduction in terms of electrons. So where electrons are concerned, we can think of redox, reduction oxidation. We can think of it as oil rig. So in this case, reduction is the gain of electrons. Part J, in the reaction, Fe2 plus acts as a reducing agent. Define the term reducing agent. So a reducing agent is a substance that is being oxidized in a redox reaction. Substance that loses electrons and itself is oxidized in the redox reaction. That would give us our marks. So we're 3 marks away from 25 marks. And they want us now in K to calculate the oxidation state of chromium in Cr2O7 2-. Our rules for assigning oxidation numbers come into play here. Or not our rules. There are some guidelines that we use. Whenever we have a radical, this is a radical, a polyatomic ion, the sum of all the oxidation numbers must be equal to the charge that is on the ion. So when we take the sum, when we take 2 times the oxidation number of chromium and we add that to 7 times the oxidation number of oxygen, we must get -2. All right. So in this case, oxygen, as we know it, oxygen in compounds has an oxidation number of -2, except when it's in peroxides. Now, this is not peroxide, so we expect the oxidation number of the oxygen to be -2. So it means we can do a little, we can write an algebraic expression and we can solve for X, but don't be scared. So we don't know the oxidation number of chromium, so we can call the oxidation number of, we can let the oxidation number of chromium be X. So if the oxidation number of chromium is X, then we're looking at Cr2O7 2-. So it means, therefore, we can say that 2 times the oxidation number of chromium plus 7 times -2, which is -14. 7 times the oxidation number of oxygen, 7 times -2 is -14. So we'll just put -14 there. All of that is equal to -2, the charge on the polyatomic ion. So in essence, we're saying then that, hey, 2x minus 14 is equal to -2. All right, don't want to leave out any steps. So 2x minus 14 is equal to -2. So we're going to put all the like terms together. And when we do that, we would add 14 to both sides. Don't want to lengthen it, but just to show where we're going. When we add 14 to both sides, we're going to end up with 2x is equal to -2 plus 14 on the right side will give us 12. -14 plus 14 on the left side will give us 0. So we'll be left with 2x is equal to 12. If 2x is equal to 12, then it follows that x is equal to 6, but not just plus 6, positive 6 plus 6. That's the oxidation state. And part L for the 1 mark, that one is looking like the L. State 1 precaution that should be taken when carrying out the experiment. And of course, we will wear protective gears. Such as our gloves and or goggles. Other one, care should be taken when working with acid. All right, and that would give us full marks, 25 marks. So that's it. Thank you for joining Chem with Chem. If you found value in this video, then just give it a thumbs up and be sure to share it with your friends. And if you haven't subscribed, then consider subscribing and hitting the bell so you're notified each time new content like this is added. So as we always say, copper later.